Hello students. So in previous lectures we have talked about the sets, subsets, universal set concept, types of sets. Today we are going to talk about the operations on sets and I will explain them with help of Venn diagrams. So let A and B be subsets of some universal set U, then first union of A and B is denoted by A union B is equal to set of those x such that x belongs to A or x belongs to B. So we have to take elements from both of the sets without repetition. Repetition of element is not allowed. By Venn diagram, if I have some universal set U, A is this set, say B is some set, then what is A union B? The shaded portion. The shaded portion denotes A union B set. Second, A intersection B, intersection of two sets. Intersection of A and B is denoted by A intersection B is equal to set of those x such that x belongs to A and x belongs to B. Venn diagrammatically, I'll denote that set by this is my universal set. If this is A set, this is B, A, B, this is universal set, then elements common in A and B is nothing but this shaded portion is A intersection B. Third operation, difference of A and B is difference of A and B is A minus B set is equal to set of those x such that x belongs to A but x doesn't belong to B. So we have to only take elements from A which are not in B. Okay. So this is nothing but by Venn diagrammatically, this is A set, this is B, universal set A minus B, this part. So from diagram you can observe A minus B is nothing but A minus A intersection B also. A minus A intersection B. Both sets are one and the same. Then symmetric difference operation. Fourth one, symmetric difference. Symmetric difference of A and B is set of those elements which lies in A or in B but not in both. So it is nothing but A union B minus A intersection B. Okay, and it is denoted by A triangle B. This is the notation for symmetric difference. This is set of those x's that x belongs to, or this is A minus B union B minus A, which is equal to A union B minus A intersection B. By Venn diagram you can observe this is A set, This is B set AB, A minus B is this part. This is your A minus B union. This is B minus A. And this is precisely A union B minus A intersection B. Now, what is the union? A, B, A union B. While talking about these operations, we require two subsets of universal set, A and B. So with help of that two subsets of universal set U, I have talked about A union B, then A intersection B, A minus B set, asymmetric difference B, and okay, these four operations we are defining. As I require two elements to define those operations, so these operations are known as binary operations on defined on universal set. And applying that operation, either union, intersection, or difference or symmetric difference operation, what new set is formed, it is again subset of universal set U. So these are binary operations on sets. We are studying all those operations from 11th standard in fact. Now again with help of the Venn diagram you can observe this operation. A union B is same as B union A. A intersection B is equal to B intersection A. Asymmetric difference B is equal to B symmetric difference A, means union, intersection, symmetric difference operations are commutative operations on universal set. But the difference operation A minus B is not equal to B minus A. A minus B is this part, B minus A will become this part here. This is my B minus A. This is A minus B. This is your B minus A. So these two sets are not equal, means difference operation is not commutative. Then one more thing about these operations. If I take third set, say C set, and if I take union of that three sets, A union B union C, and if somebody take A union B union C first, so B union C will be this part union A. A union B union C. So these two sides are equal, means union operation is associative. Likewise, your intersection operation is also associative operation. You can observe that difference operation is also associative operation on universal set or collection of subsets. These are binary operations in which difference operation is non-commutative, other operations are commutative as well as associative operations. That are the properties. Now, complement. For A subset of U, complement of A complement is denoted by this symbol or A dash. It is a set of those X belongs to U such that X doesn't belong to A. So this is precisely U minus A set. So this is my A subset of U. Then what is your A complement? The shaded portion is nothing but A complement. Now if I relate given set to its complement, it is also subset of universal set. A is relating to its complement is also one operation, but to talk about the complement of a given set, we require only one set. That's why given set related to its complement is unary operation, as we require only one subset. So laws of operations. So for every subset of inertial set U, first A union B is equal to B union A, and A intersection B is equal to B intersection A. So these are known as commutative laws. Commutative laws. Second one, A union B union C is equal to A union B union C. And for intersection, A intersection B intersection C is equal to A intersection B intersection C. These are known as associative laws. Means union, intersection are commutative operations, union, intersection are associative operations on the collection of subsets. Third law about these sets for A, B, C subsets of U. Distributive laws. A intersection B union C is equal to A intersection B union A intersection C, and A union B intersection C is same as A union B intersection A union C. These laws are known as distributive laws. Union distributes over intersection and intersection distributes over union. Fourth law, De Morgan's laws. These are very important, which are already studied. Complement of union of two sets is equal to intersection of their complements, and complement of intersection of two sets is equal to union of their complements. These laws are known as De Morgan's laws. Other important laws. A union A is always equal to A, and A intersection A is equal to A for any given set. Then identity laws. Six, identity law. A union phi is always equal to A implies phi is identity. Okay, for every subset A of A belongs to U implies phi is identity for union operation, and A intersection whole set universal set U is always equal to A for any A subset of U. What this implies is your U is identity for intersection. So you can take examples, and firstly with Venn diagram you can verify all those laws and go through the exercises. You will get some expressions given in terms of union, intersection, difference, symmetric difference, and whether two sides are equal or not. Go through that examples also. So here I am not interested to solve that examples because you already studied so many examples on union, intersection, or associative law, commutative laws in 11th standard. Or you can follow 11th standard books for sets also. Our interest is to study relations and then equivalence relation. Okay, on this there is one more concept is that power set. What I mean by power set? If X is a set, then collection of all subsets of X is called as power set. It's called as power set of X. It is denoted by P of X. Okay. Example. Given set X and its power set. So first one, X is equal to 5. Number of elements in power set of X. So power set of X contain just empty set. If X is 5, then X has how many subsets? Just empty set is subset of empty set. So power set of X contain only subset 5. So number of elements in 1. Power set of X. Second, if I take X is equal to say singleton A set, then what will get here? Power set of X. Okay, this is your power set of X. Power set of X in this case. Now first the empty set is subset of itself, and then in empty set I am inserting A, so I will get singleton A. So I will get 2 subsets. Third, if I have X is equal to 2 element set A, B, for 1 element set there are 2 sets. So for A, I will get corresponding to A, I will get this as a subset, phi A. And then inserting B in A, B in phi, I will get B, and your in A, B will get AB. Right? So we will get 1, 2, and here 4. Now third, fourth, if X is equal to say 3 element set ABC, I will get this collection as a set subsets of X here also. So what is power set of X here? These 4 elements must be there, phi A, B, AB. Then what I am doing? I am inserting C here, AC, BC, ABC, and then I will get 8. So you can observe this is 2 raised to 0, this is 2 raised to 1, this is 2 raised to 2, this is 2 raised to 3, right? Now if I take 4th element D, if I insert 4th element D, then your power set of X contain all those subsets with 3 element set ABC, and inserting D in every element here, every subset here, I will get additional 8 subsets. That is D, AD, BD, ABD, CD, ACD, BCD, ABCD is full set. Okay. So 5, X is equal to ABCD, power set of X is equal to, and here we will get 16 is equal to 2 raised to 4. Okay. So note If number of elements in X is equal to K, then number of subsets of X, power set of X contain 2 raised to K subsets of X. And just proof is by mathematical induction. Proof is by mathematical induction. So this is about power set concept. Very important for the further study of relation, then finding number of relation defined on the given set, etc. Okay. Now our aim is to talk about the relation on sets. So we'll define Cartesian product now. Cartesian product. If A and B are non-empty sets, then A cross B is set of ordered pairs AB where A varies in A and B varies in B. Is called as Cartesian product of A and B. Cartesian product of A and B. For example, if A is equal to say ABC, B is equal to say 1, 2. If I take this, then what is your A cross B? I'll take A1, A2, B1, B2, C1, C2. There are 6 elements. B cross A also contains 6 elements. 1A, 2A, 1B, 2B, 1C, 2C. So from this, these two are not equal, means A cross B not equal to B cross A. Okay. Note, if number of elements in A is equal to say R and number of elements in B is equal to S, then number of elements in A cross B is equal to every element of A forms pair with every element of B. So first element forms pair with each of element of B. So if B has S element, so first element with all S element gives us S pair, second element gives us S pair, and so on. Rth element gives us S. So S plus S plus S R times, so RS, R into S. And number of elements in power set of A cross B by previous result, it becomes 2 raised to RS. Okay, that is A cross B has 2 raised to RS subsets. This is the important result for relation. So we'll talk about now relation. If A and B are non-empty sets, then any subset R of A cross B is said to be relation from A to B. Is said to be relation from A to B. A to B. For example, previous one, if I take, if A is equal to say ABC, B is equal to 1, 2, then first R1 is equal to 5 is subset of A cross B. This relation doesn't relate any element of A to any element of B. A to any element of B. So empty relation is also defined. In our usual life, if I take A to be set of all males, B to be set of all females, okay, or in our class, if A is set of all boys, B set of all girls in our class, and then I am taking R to be relation containing those pairs AB in such a way that A is husband of B. As you are of age 18 years, so no one is married with any other. So no one is husband of other girl from this class. And that's why that relation doesn't contain any pair. So it becomes empty set. So empty relation is also defined on the set. Okay. Second, if I take R2 is equal to, say, pair A2, B1, only these two pairs if I take. This is also relation. If I take A cross B, R3 is equal to, say, A1, B2, C1, R4 is equal to. If I take A1, then B2, B1. If I take like this, okay. Note, number of elements in A is equal to 3. Number of elements in A, B is equal to 2. Implies number of elements in A cross B is equal to 6. And therefore, number of elements in power set of A cross B is equal to 2 raised to 6. What is 2 raised to 6? Is 64. 2 raised to 6 is 64. Is it clear? Implies there are 64 subsets for A cross B. That is, there are exactly 64 relations from A to B. From A to B here. Among these, I have written some relations from A to B. Among that, we have written few relations from A to B. Only I have mentioned 4 relations. A cross B itself containing 6 pairs. A1, A2, B1, B2, B, C1, C2. That is also one relation containing maximum number of pairs. That is one relation from